All right, today we're going to map out a family tree. But, not for some royal family or a famous dynasty. Nope. We are diving deep into the family tree of inorganic chemistry, tracing all the relationships between the compounds that literally build our world. So, let's go meet the ancestors. But first, a quick question for you. Think about the soap in your shower, the batteries powering your phone, and the fertilizers that grow our food. On the surface, they seem totally unrelated, right? Well, what if I told you they all share a common chemical ancestor? Because that's the answer. They are all key members of this huge, sprawling family of inorganic compounds. It's like this invisible network that connects so many things we use and rely on every single day without even thinking about it. So, what even makes a compound inorganic? Well, it usually boils down to two things. First, they generally come from non-living stuff, like minerals you dig out of the ground. And second, they almost always lack those carbon-hydrogen bonds that are the absolute hallmark of organic chemistry. Now sure, there are a few exceptions, like carbonates, but this is a really solid rule of thumb.
Okay, so every family tree has to start somewhere, right? And for our chemical family, that starting point is the oxides. You can think of them as the great-great-grandparents of the entire clan. They're the progenitors, where everything else branches off from.
And what is an oxide? It's actually pretty simple. It's just a binary compound, which is a fancy way of saying it's made of only two elements. And one of those two elements is always oxygen. That's it. This simple little partnership is the foundation for pretty much everything else in this family. But here's where it gets interesting. These oxides kind of have four different personalities. See, when oxygen teams up with a nonmetal, the oxide tends to be acidic. When it pairs with a metal, it's usually basic. Then you get the really flexible ones, we call them amphoteric, and they can swing both ways, reacting as either an acid or a base. And finally, you have the neutral ones, who just don't pick a side. This is really the first big split in our family tree. So this is the really crucial takeaway here. Depending on what that oxygen bonds with, these original progenitor oxides give birth to the two main and often competing branches of the entire family, the acids and the bases. And that brings us right to those two great branches. If oxides are the ancestors, then acids and bases are their children. And let me tell you, they each have very distinct and often totally opposite personalities. So let's meet them. Our whole understanding of what an acid is has changed over time. The story really kicks off with the Arrhenius definition. He said an acid is anything that when you dissolve it in water, releases hydrogen ions. That's H+. It's a fantastic starting point, but it's a little limited because it only talks about what happens in water. So next up, the Bronsted-Lowry definition came along and broadened the whole concept. It says an acid is anything that can donate a proton, which, let's be honest, is basically just a hydrogen ion anyway. This definition is way more inclusive because the reaction doesn't have to happen in water anymore. And finally, we have the Lewis definition, which zooms out even further. A Lewis acid is defined as anything that can accept a pair of electrons. It's a great example of how our scientific understanding grows, right? We went from a very specific case to this big universal principle all about how electrons behave. The different personalities of acids and bases become super clear when you see how they act. Acids, for example, taste sour, think lemon juice, and they'll turn blue litmus paper red. Bases are the complete opposite. They taste bitter, turn red litmus blue, and they often feel really slippery or soapy. And smack dab in the middle of this chemical tug-of-war is the number 7. On the pH scale, which is just a way to measure acidity, a 7 is perfect neutrality. It is the exact balance point between the two branches of the family. Think of pure water. Okay, so what happens when these two opposing branches, an acid and a base, finally come together? You might think they'd just destroy each other, but no. Instead, they create something totally new, the next generation in our family tree, the offspring, we call salts. So chemically speaking, a salt is an ionic compound that gets made when the hydrogen part of an acid gets swapped out for a metal ion, which usually comes from the base. I mean, regular old table salts, sodium chloride is the most famous one, but believe me, there are thousands and thousands of others. So how does this happen? It's all through a process called a neutralization reaction. It's a super simple 4-step story. You start with an acid, you add a base, they react, and they neutralize each other's properties. And what do you get at the end? A salt and, almost always, water.
It's like a perfect chemical peace treaty.
But just like in any family, not all the kids are identical. You have your normal salts like sodium chloride, where the acid and base have totally and completely neutralized each other. But you can also have acidic salts or basic salts, which just goes to show that sometimes the kids inherit a few more traits from one parent than the other. All right, so we've mapped out the whole family. We started with the oxide ancestors, met the acid and base children, and their salt offspring. But why does any of this matter? Well, it matters because this family is hard at work all around us, in pretty much everything we do. The acid branch of the family is incredibly busy and, frankly, super powerful. Sulfuric acid is chugging away in car batteries and helping grow our food. Our own stomachs use hydrochloric acid for digestion. And nitric acid is another major player, used in everything from, again, fertilizers to explosives. And the base branch is just as essential. Sodium hydroxide, that's the powerhouse that gives soap and drain cleaners their cleaning muscle. We use calcium hydroxide in the mortar that holds our buildings together. And ammonia is a total workhorse. You'll find it in fertilizers, cleaning products, you name it. And here is where it all comes full circle. If you've ever looked at a bag of fertilizer and seen NPK on it, you are looking at our inorganic family hard at work. Those letters stand for nitrogen, phosphorus, and potassium, 3 absolutely essential nutrients for plants, all delivered in the form of these very compounds we've been talking about. So look, if you want just one simple way to remember all of this, think of it this way. Inorganic chemistry is basically the chemistry of everything except most carbon compounds. It's the chemistry of minerals, of metals, of the fundamental building blocks of our entire planet. From those oxide progenitors to the acid and base branches and all their salt offspring, this chemical family is absolutely everywhere. So the next time you use soap or drive past a farm, you'll know the family tree behind it all. Now that you've met the family, what other connections are you going to start seeing in the world around you?